Hello, I'm Rich Eisenberg, Editor-in-Chief of Inorganic Chemistry. As part of our 50th anniversary celebration, we're having interviews with leaders in inorganic chemistry, the field, and how they've impacted inorganic chemistry, the journal. It's a distinct pleasure to have Professor Ken Raymond from UC Berkeley as our visitor today. Ken is a real leader in the field of inorganic chemistry. He's been notably involved in bio-inorganic chemistry, which we'll find out about shortly, and other areas as well, including the transuranium elements also. He has received numerous awards, including the DOE E.O. Lawrence Award, the Alfred Beta Award from the American Chemical Society for bio-inorganic and bioorganic chemistry, the ACS Award in inorganic chemistry. He's been elected to both the American Academy of Arts and Sciences and more importantly, the National Academy of Sciences. Ken, it's a distinct pleasure to have you today, and welcome.
Thank you, Rich.
Let me start with the early Raymond years, and how did you get into the chemistry that that you do? What were the influences that moved you in this direction?
Well, I am a fourth-generation Oregonian, and my early childhood was spent mostly in small towns, and I went to a two-room school for some time. And I skipped to the 5th grade, and all of that, I think, helped lead me off into different directions than certainly my immediate family would traditionally have taken me. So early in high school, in a suburb of Portland, Oregon, I had the very good fortune of having an outstanding chemistry teacher. I was already by then very curious about science, and I'd played with a chemistry set since I was 11 or 12 years old. And I found playing in a laboratory was really exhilarating. And I think already by then I'd made a decision to have a future somehow in science. I don't think at that time I dreamed of being a professor of chemistry, but something in science.
And then from there you went to Reed College, I believe.
Yes.
And was your interest into inorganic chemistry peaked at that time, or when did that happen?
Reed College really changed my life because I'd been something of a bad boy in high school, and so I actually had, I think at one point, less than a C average. So I applied to one place, Reed College, and they took chances on people. If you had a very high test score or your teachers were recommending you. I mean, my best friends at that point, at the time I was in my senior year in high school, were my teachers. And so Reed accepted me, and it really, it changed my life. I met Arthur Scott, who is a famous professor of chemistry there, and he did nuclear chemistry. He was involved in neutron activation analysis. And so at that point I was going to be a nuclear chemist, and I was very proud that I think at the age of 18 I was the official Atomic Energy Commission manager for their hot lab, so I had to do weekly swipes and keep a log and so forth. And then in due course, there was a summer NSF-funded institute for inorganic chemistry that was at Reed for 2 years, 2 summers. I was the only Reed student the second summer, but a number of very prominent inorganic chemists, Harry Gray, Fred Basolo, all of the top inorganic chemists that came either that summer or the previous summer, and that was when I first met Fred Basolo, and it literally made me decide I wanted to be an inorganic chemist, and this is the guy I want to do my PhD for.
Now you work with Fred at Northwestern. I know you also worked with Jim Ivers at that time. Fred is, as we both agree, one of the real giants in inorganic chemistry. So let me ask you to tell us a little bit about what the qualities were Fred brought to the table? What was it that made him such a great person? And I should also mention, Fred was a very strong advocate for the journal Inorganic Chemistry and helped to get it started.
Fred, I think, shared some qualities with Henry Taube, both of whom I admired greatly and still do. They were deceptively simple in their approach to chemistry and perhaps to life, but at least the way they came across. Fred had a way of presenting information that I thought was very clear and direct. He was innovative in the way he approached both synthetic chemistry and especially mechanistic chemistry. At the time, I was in his research group, and prior to that, almost everything had been mechanisms of inorganic reactions, and his famous textbook with Ralph Pearson was that title. I think I was the only student in Fred's group, at least at that time, who never determined a rate constant in the course of his PhD research. My research was on making things, and I had made some 5-coordinate complexes, and Jim Ivers was a newly arrived full professor who, from Brookhaven, who could help me solve structures. And I think it was also part of Fred's generosity that he encouraged this student that I think he probably thought was an up-and-comer to work jointly with Jim Ivers. And for me, it was a tremendous benefit because these two were so complementary in their approaches.
From Northwestern, then what?
So, late in my second year in graduate school, I had an interview with Fred where we talked over my science, and he said, "Ken, things are going pretty fast for you. You should be thinking about a job." And I was a little nonplussed, and I said, "Well, what do I do?" And he said, "Well, first, do you want to go into industry?" "Not, right?" No. I said, "No." And not into the national labs? "No." "So that's academics?" "Yes," I said. "What do I do?" He said, "Don't worry, I'll take care of it." Next thing I knew, I had 3 phone calls from first UC Riverside, then Caltech, then Berkeley, inviting me for interviews. So I interviewed at Berkeley in the middle of my 3rd year in graduate school, and it was in 1960, beginning of '67, and I was officially appointed to the faculty in July of '67, when I didn't yet have my PhD, and arrived on the Berkeley campus in December of '67, and then received my PhD officially in June of '68.
Very different situation than we find today.
Yeah, my students hate these stories.
We'll get back to that in a little while, but let me ask you, what are the key themes that and ideas that run through your research today?
Well, I think throughout it's been metal ligand selectivity. How do you design ligands that will be selective for particular metal cations? And that followed on my training as a coordination chemist, and both the synthesis and the structural aspects of what I did in my training, I think, have carried through in my research interests.
You are one of the leaders in bioinorganic chemistry, and I know that one of the early subjects that you started to look at was the binding of iron and siderophores, which I think builds on exactly what you said, coordination chemistry. But tell us a little bit about that.
Well, I had no background in biochemistry or biology at all, but I was interested in this new word, bioinorganic chemistry, and I had gone to a workshop, actually, I think in the summer of 1969, and which was held in Blacksburg, and which may be the world's first bioinorganic chemistry meeting. But it was still, it was just curiosity at that point. But I was in charge of seminars the following year, inorganic seminars, And I did something which at the time was quite unusual. I invited my colleague Joe Nealons from the biochemistry department, who was working on siderophores. He's one of the, I think, two main figures internationally in the early characterization of siderophores. And so it was not so common in those days to have an inorganic chemistry seminar from somebody in biochemistry. Anyway, Nealons showed us the structure of ferrochrome, ferrochrome A, which is chiral. It has 3 hydroxymate groups and it wraps around the iron. But there are, of course, 2 ways to wrap around the iron, delta or lambda. And I asked him if that made a difference to the microorganisms, and he said, I don't know. I don't think anyone's ever thought about that. And so I literally took almost 6 months off, which is a very risky thing for an assistant professor to do, and read and read and read and read. And I wrote a proposal to the NIH and got 2 years' worth of funding. And that started my siderophore research. And for about at least 10 years, I was the only chemist working on siderophores. Everybody else in the field was either a microbiologist or a biochemist. But I was specifically interested in the coordination chemistry of the siderophores and how that affected their transport, recognition, uptake into bacteria.
Another area or another subject that you've looked at extensively involves luminescence and the rare earths and how you could use them for biological applications. Tell us a little bit about those.
Well, in a way, it flows from the siderophore chemistry, because what fascinated me about siderophores is that you have these small molecules that are highly selective for ferric ion, specifically high-spin iron 3. And so it's a very hard metal ion. It likes oxygen anions. And so then that carried forward into, if you complexing lanthanides, again, they're oxophiles. You want higher coordination numbers, and then additional properties that have to be built in, like good light absorption, efficient energy transfer from the ligand to the metal. And I have to say there, I've had a fair component of serendipity as part of the research, but once you observe something, then you need to follow up on it, and practical compounds have resulted from that.
Yeah, would the same thinking go into some of the work that you've done that involve the actinide elements? And there are different challenges there, but would the same fundamental thinking be at work here?
Yes, and in fact, that preceded by quite a long time the lanthanide luminescence work, and what's now called the siderophore hypothesis. The idea was that plutonium's toxicity has at least as much to do with its chemistry and biochemistry as with its radiation properties. It's an alpha emitter, but it, as a contaminant, looks enough like iron so that in the mammalian system it's complexed by transferrin, the serum iron protein that moves iron around, and ends up stored in ferritin and delivered to iron storage sites, which is not where you want alpha-emitting radiation. And so the idea was to make higher coordination numbers, in this case octadentate chelators, that incorporated the same functional groups found in the siderophores. And it works. So there's a large-scale NIH effort to develop agents for emergency clinical use in actinide decorporation based on that chemistry.
You've had very large groups to accomplish all that you have, how many students and how many postdoctorals over the years have you mentored?
88 PhD students and 102 postdoctoral fellows and a large number of undergraduates.
Now, to support, well, there are 2 questions here. One involves how do you take care of feeding all the mouths that you have? The other is how do you take care of all the mouths and manage the group in an efficient way? Let me ask you both of those questions, but let's begin with how do you handle a large group, and what advice would you have for young faculty who are just beginning who would like to emulate you?
Well, to some extent, this is a bit like Topsy. It just grew. The but I would say I don't really have one large group, I have 5 small groups. So my research group calls this Kenneth 10. Every day, usually at 10 o'clock, I have subgroup meetings. So on Mondays it's one kind of chemistry, on Tuesday another, and so forth. Some people come to more than one of those. New members of the group usually come to all of them for a few weeks, just to get to know everyone. But these subtopics, if they're to drop below 2 or 3 people in them, it would be below critical mass. And so if my research group is to get a lot smaller, I'm going to have to jettison one or more of these areas, and I've been reluctant to do that heretofore.
Now that's in terms of then the management, we have the smaller groups. In terms of advice for prospective faculty, what would you tell somebody, a young colleague coming in today, in terms of how to start?
To start with, don't try to emulate directly somebody like me. If you don't have the best pair of hands in your early starting group of maybe 3 or 4 or 5 students, then your employer made a mistake. So utilize the fact that you're a really good chemist, whether it's synthesis or whatever kind you do. And so don't get out of the laboratory too early. And that's a temptation, especially these days, because it's so much harder, I think, to get early funding. But the compensation for that has been that universities are typically providing much larger startup packages. And so in the first couple of years, while you're training those first students, get some papers out from your own research as the group builds. And I think it's also a tremendous incentive for the group. Early students are very excited about working elbow to elbow with their supervisor.
Another area that you're working on now, also in, I'm not sure I would say a new area, it's had a decade plus activity, and that involves some collaborative work that you're doing with Bob Burg. Tell us a little bit about that chemistry.
Well, that first started about 15 years ago as a purest of pure research project where I wanted to make supramolecular clusters. And it literally started with me staring at ferritin, which I've worked on. It's the iron storage protein. And it's a supramolecular complex of 24 proteins, in principle identical, that cluster together to form this beautiful octahedral structure with a very large cavity inside that ultimately can hold a little piece of rust to store iron. And in analyzing the symmetry of that and thinking about it, I came up with a model for what I at first awkwardly called coordination number incommensurate cluster formation. Unsurprisingly, that hasn't survived a terribly long time. But the idea was that the interaction of these different coordination numbers can only occur if the axes between the symmetry numbers are specific angles. And if you build the subcomponents so that those angles and only those angles can be matched, then the cluster has to form. And using metal ligand bonds, specifically hydroxymate first and then catacholate bonds, those clusters formed. And then about 6 years later, the idea was what to put inside the cluster, and my friend and colleague Bob Burg, who's an expert on CH activation, the idea was that this cavity, which is hydrophobic, should be a good host for some of the organometallic cations that Burgman has pioneered in doing CH activation. And the goal was then to do non-aqueous chemistry in aqueous solution with these inside the clusters. And then that's branched out from there so that a number of other directions have taken place. So in a way, I think this has been an illustration of the very best kind of collaboration. I would never have done the catalysis chemistry without Bob, and Bob didn't have the clusters. And so this project has been the best kind of collaboration.
That's great. That's great. And it also makes for very good movies. I should say that there is a spectacular movie that shows how molecules can move into and out of these different clusters. So one of your students did that?
Yes, and we'll be glad to share it with Inorganic Chemistry.
Okay, well, we'll look forward to it, maybe even as part of this interview. Ken, let me ask you about whether there was a particular special moment, we might call it a Eureka moment, when you suddenly realized that you have solved a problem or found something new or achieved a level of understanding that was not possible before. Those are very special moments. They give you a great feeling of satisfaction and a sort of a great scientific high that only a scientist can appreciate. Well,
two, I'd point to, I guess, one was the siderophores, and that blossomed rather slowly, but it became clear early on that a coordination chemistry approach where we could manipulate replacing iron with something kinetically inert like chromium. This could enable biochemical experiments, transport experiments that couldn't be done otherwise. And the area that we just talked about, the cluster chemistry, that was kind of a Eureka moment and has continued to be, both of these areas have continued to be very productive, and I think were authentically good ideas. In terms of a crystalline Eureka moment, a very early one was determining the structure of uranosine. I mean, that wasn't my molecule, that was Andy Streitweiser's accomplishment. But for technical reasons, it was hard to solve in 1969. And so I had a new technique to use, armed with a library of computer programs that I had carried from Jim Ivers' lab. And so in one glorious afternoon with a styrofoam box that one did in those days, as you will recall, I could build up the structure of this from a difference-Patterson map.
I know there's a difference between what is perhaps the most profound and yet the most personal, satisfying research moment, and when you're starting out doing crystal structures, as we both did, you know, seeing a molecule come together from a different synthesis or something like that is really very exciting. Yes. Yeah. Let me turn attention to advice that you would have for young scientists today in terms of communicating their science. Your papers have been they're paragons of scholarship and insightful thinking, and what would you say to young scientists starting out? How would you advise them about communicating their science?
Well, I think there's a temptation for ever more for hype, and I think it's absolutely essential to communicate and to advertise your science, and you don't want to just count on the fact that people will read it and fully understand everything. But on the other hand, you don't want to oversell it either. And if the science is good and you present the story well, the community will take note. So I think it's important to have the fundamental facts right. I think it's so easy today with computer-generated pictures, with easy access to rather high levels of theory, to ignore the elemental analysis that doesn't fully agree with the story. And one shouldn't do that.
Thank you. I agree with that as an editor with regard to elemental analysis. Compare the funding picture that you encountered when you started out with the one that you see new faculty today struggling with. How has it changed? And again, what advice would you give to new faculty about trying to secure the funding needed to do their science?
Well, we spoke earlier about difficulties of funding and the importance of startup packages that are sufficient to carry somebody through for 2 or 3 years at least. It is alarming. I think the average age for new investigators at the NIH within the last decade went over 40. And the National Science Foundation, I think, is increasingly, primarily because it's instructed to do so by Congress, but is increasingly focusing on issues other than what I would call pure science. And I was very fortunate. I had an NSF grant, a small one, but it was mine, in my very first year. So I applied when I was 25, and I had my own NSF grant when I was 26. And I'm eternally grateful to the NSF for that. It made a huge difference in the start of my career. I think as a community, we have to continue to focus on funding the best science and making sure that we bring in the best young scientists with independent funding. There's a built-in bias. I mean, you know, old guys like me that have lots of publications, there is a certain track record. And so it's important that we take risks on young people and make sure that they can compete in the funding process.
In part, then, it's a responsibility of the scientific establishment to try to lobby for making the pie bigger, making more funds available for research, and particularly for new faculty members.
As both NSF and NIH have done at various times in trying to have set-aside programs for new investigators, and I support that.
Okay. How do you picture that chemical research will change over the next few decades, and how do you think what enduring qualities will we need to keep in our science to make sure that we move forward in an intelligent way?
Well, I mean, the word complexity is perhaps overused, but I think it can hardly be overused if you look at trends. In chemistry, the focus has gone from small molecule to larger interactions, and of course, whether that's nature or synthetic materials, nature is at least as good an engineer as she is a chemist, and so the properties of both natural and synthetic materials have at least as much to do with their macroscopic interactions as with the individual microscopic or molecular components. And of course, the polymer chemists have known about that for a long time. Whether every other methyl goes up or down makes a huge difference in the properties. Only now are we starting to be able to do that in making synthetic tooth material, for example, that can be used in patients. I think there's going to be a tremendous increase in medicine in the use of artificial materials, maybe biogenic rather, but also perhaps purely synthetic, as in the bone example that I gave.
The separation, well, one of the things you said, which let's dissect just a little bit, and that is fundamental interest versus practical application. Now, as we make these larger structures and this notion of organization and self-assembly, we want to do this in terms of fundamental interest, but we also want to do it in terms of practical application. Does the practical application drive the fundamental interest too much, or does it lead to derivative science, or what?
I don't think so. I'll give one specific example in an area that I'm interested in that we haven't touched on very much yet. In actinide chemistry, theory especially for 5Fs, but also for 4F systems, was not terribly useful until about the last decade. It's very complicated, difficult, high levels of computation, large amounts of computer time required. Now, quite good calculations can be done, and it really informs the associated synthetic chemistry and properties. And I think that is synergistic. And you know, it's very exciting, the Kondo effect, the interaction of F-electron spins with surroundings, which isn't just in the solid state, but also examples in molecular species. And then from the practical side, it's clear that for nuclear chemistry to be a component of future energy program, which I think most people who are interested in energy these days would say will be at least a near-term requirement, you need a new fuel cycle. We can't use up 5% of the nuclear fuel and convert 95% into waste. We need to do the reverse of that. And that's going to require new kinds of chemistry. And I think these capabilities are feed in both directions. They feed each other in both directions.
Do you think that inorganic chemistry plays a role in terms of the environmental impacts and feasibility for nuclear energy?
Absolutely, because it's going to require a lot of new material science, whether these are nitrides in the fuel components or other more advanced materials. And then the separations processes. Most of the nuclear industry has relied on chemistry that essentially dated from the Manhattan Project. And there have been spectacular advances of the extraction of cesium, which was developed at Oak Ridge from waste fuels, is one very good example. I think we'll see much more of that kind of chemistry being applied in the nuclear power program.
Let me turn attention to the question of publications. You began your career, independent career, in the late 1960s. And that was just a few years after the journal started. When was your first publication, do you remember, in inorganic chemistry?
I think it probably was 1969, but I have every volume of inorganic chemistry up until the last years when I gave up hard copies. The first 2 years of inorganic chemistry, which I read, but I wasn't yet a professor, but I inherited those from a colleague who retired. So I don't recall exactly, but I think it was probably about 1969, certainly by 1970. Did you look this up?
No, I didn't. I didn't, actually. I actually thought they were the pentacoordinate, or was that in Jack's?
So my first pentacoordinate stuff was with Jim Ivers, right. and then I published a couple of papers in inorganic chemistry, and it would have been about the time frame of 69, 70.
Yeah. Was that the pentocyanonickel?
I did some more work on pentocyanonickel independently, and I also did some work on the 5-coordinate copper systems. And then we isolated cobalt cyanide complexes, but those were a little later. Those would have been early 70s. And much of that chemistry was published in inorganic chemistry.
How have you seen the journal evolve from the time that you started until today?
I would say 2 areas, bioinorganic chemistry, which has its own associate editor, and materials. And I think it accurately reflects the ever-broadening scope of inorganic chemistry. Organometallic chemistry, of course, was a huge expansion early on. That was already well underway in the 60s. The bioinorganic and materials components, I think, were later developments.
I should point out that we actually have more bioinorganic chemistry than one associate editor handles. In fact, there are several associate editors who are able to handle bioinorganic.
Well, I know one in particular. Yes, so.
Former student, that's Vince Pecoraro, and is a former student of Ken Raymond's. In this world of increasingly interdisciplinary research. What are the real advantages that you see for people to publish their work in inorganic chemistry as opposed to, let's say, in journals that are intended for smaller groups working at the periphery of inorganically related science?
Well, as a general philosophy, I believe in choosing the audience you want to reach by the journal you want to publish in. And the advantage of inorganic chemistry is that inorganic chemists around the world read the journal, and it's a certain level of expertise. There are some journals that are for a mass audience, and it's really not appropriate to have the details that the experts will want to see and will understand. With inorganic chemistry, you're addressing the experts, and you can make your full case with all of the data that supports it. And I think that both for the immediate progress of science and for archival purposes, I think that's really important.
How do you see scientific publication changing in the next decade from what it is now? And clearly it's different from what it was 15 years ago. How do you see people getting their information, their scientific information, differently from the way they did?
Well, this is an amazing change and rate of change. I wrote my first papers and had them typed by a secretary on a Selectric typewriter. My PhD thesis was typed that way, and if you made a mistake, you had to go back and snowpake it over. So word processors changed that enormously. A similar revolution has been the ability of the internet with regard to publishing. 15 years ago, some postdoc finished and went back home to Italy or something. You're relying on the mails to send things back and forth. Now, overnight, in their time, they have read the paper and send it back for you to read the next day in your time. And so the efficiency of that has gone up tremendously. And then the virtual library. I used to spend many Saturday mornings in the chemistry library. I don't do that anymore. I can't remember the last time I looked up an article physically. Almost everything is accessible on the web. And so I must say, and maybe this is just because I'm old-fashioned, I still like to print out an article when I'm proofreading it, because having the paper in my hand and the ability to scribble on it, I still find valuable. But otherwise, pretty much everything I do is on screen. What will come in the future? I'm sure that within the next few years, I won't be trying to find the file. I'll be asking my computer. My computer will respond with questions spoken to me, and the instructions will go back and forth that way, in an interactive vocal interface.
I'd like to see that. I think we both would, going forward, to keep ourselves well organized. Is there anything that you want me to, go back and ask you about?
Well, I think I touched on mentors. I mean, that's one thing I wanted to make sure that, and maybe one thing. So I won the Volume Award at Reed 3 years ago, and had the good fortune of having my high school teacher, who's still alive and well, attend, and 2 of my professors from Reed, and I invited them out to dinner that night, and it was a wonderful moment of recognizing one's teachers.
With that, I would like to thank you for coming and spending some time with us today, and I would like to thank you for joining us for this very interesting interview, and I hope to see you here again for the next one of our interviews with leaders from inorganic chemistry. Thank you.